Hey, circuit students. Well, here we are again, trying to condense two rounds of class into one, so that so the college isn't complaining as much about never mind what that, so that I get less complaining about the college is the main thing, and maybe so you don't have to watch quite as much video of me as a secondary thing. Okay, so I'm going to get to the questions that folks have. All right. Most of these are pretty straightforward. This is a little bit, probably people's questions and stuff are a little more mathematical. I don't need a bunch of demos this time. First thing, the difference between AC motors and generators and DC motors and generators. Remember in the video that I did last time about the motor and the brushes and stuff, okay? The brushes are there in that motor because when you have a wire with current in it in a magnetic field, the field pushes it one way. Okay, so in that video it pushed the wire like this. Well, what happens if like when I had that magnet before and the wire was hanging across it and I turned on the current, it would push it over here and then sort of stay. Okay, so what you would need, let's suppose you wanted to make a motor that consisted of oscillations like this, so they push the wire and then it swing back, and then and then push it again and swing back, and push it again and swing back. You need some sort of switching mechanism to turn the current off so that it can swing back, and then turn it back on so it's pushed again, and then turn it off so it can swing back, turn it back on so it's pushed again, and that would provide you a way of driving the wire back and forth, back and forth. Well, imagine instead I had an AC current going through that wire, and that the current was synchronized to the swinging, so that the current when the wire was here, it was pushed this way, but then by the time it came back, instead of the current running in the same direction, so that the wire just wanted to stay, it was running the other direction, so now it got pushed the other direction, and then it got pushed again, and so that alternating flow of current was helping to make the thing go. Well, then you wouldn't need a switching mechanism. Okay, you wouldn't have to have some sort of switch. So you can build an AC things that don't require that commutator in there that keeps switching the current to make the motor turn. Likewise, when I spun it. All right, and I'm going to recommend you go back and take a look at that video from last time. These are I got them all linked on the class webpage. But I recommend you go back and take a look at that video from last time and watch when I spun it how you got a DC essentially current out of it. Well, if I didn't have those brushes, that commutator arrangement there, what I would have is it would be an AC. Okay. But the natural thing that you're going to generate from a rotating motion is an AC current. So you don't need as much mechanical switching, or you could do this, do some sort of electronic thing. But traditionally you don't need all that mechanical doodah there to keep switching the current and maintaining a direction. So that's a big difference between AC and DC in motors and generators. Right? Now, another question that was asked about the AC was about the alternator in a car. Okay, an alternator versus a generator. So a generator again is going to produce a DC voltage. This is once again the natural thing you're going to get if you have a coil of wire and you spin a magnet inside of it, okay? Or you have a magnet, you spin the coil inside of it. The natural result of a rotating motion is a sinusoidal output. We're gonna have a project on this. I've got one up currently. So natural result of rotational motion is sinusoidal output. So to get a DC generator, again, you have to either have some sort of electronic or electromechanical switching arrangement to make it DC. In a car, the alternator, does it, someone asked, does it charge the battery all the time? And Loosely speaking, yes. Okay, so in older cars, I had an old Triumph Spitfire, 1971. Okay, I bought it old. I bought it when I was in high school. It was kind of cool. It was a piece of junk by modern standards, but it was a convertible and it looked cool. So, but when you revved the engine, the voltmeter would rise up and down, right? Because as you spun the engine, it generated, the alternator was producing more voltage. Okay. You don't see that. You don't see that like so much that your headlights like brighten up at night when like if you're at an idle, your headlights get dimmer, and then you step on the gas and they brighten up. And then if you turn off the engine, they go dimmer still. Because we've gotten better at figuring out how to regulate voltages and stuff like that. But yes, the bottom line is that your alternator is on a belt on your car and it's spinning all the time. If it's spinning all the time, it's going to generate some amount of voltage, and it will charge your battery. If your alternator goes out, then what happens is hang on, my sorry about that. My computer's telling me its battery's running low, so I have to pause and plug it in. Okay, so anyhow, the alternator is always spinning, always generating a voltage, it's always doing at least something. So it's always maintaining a charge on the battery. If your alternator went out, that's what I was going to say, then you would drive on your battery to supply power for the electricity for the car, but it would eventually run down and die. Okay, because the alternator is constantly supplying charge to it. All right. Okay, so next thing is RMS. There were a number of questions, and probably this is the thing that the most people asked about was the root mean square averages. Okay, so the idea is that in an AC current, or an AC voltage, so if I make a graph, voltage here, time here. Well, in a DC, your voltage is steady. So let's say that it's 10 volts. So in DC, voltage is steady. But in an AC, let's suppose we would have a voltage that oscillates back and forth between positive 10 volts and down here, negative 10 volts. So here's a graph of an AC voltage. What is the average voltage here? Well, it goes up to 10 volts, goes down to negative 10 volts. It goes up to 10 volts, it goes down to negative 10 volts. So on average, it is at 0 volts. Okay, my average voltage is equal to 0. So likewise, my average current is equal to 0 in an AC setup. All right. So, gee, so you say, well, what's the average voltage that's coming out of that outlet down there? 0. What's the average current coming out of it? 0. Well, that would make you think, well, gee, if there's no current and there's no voltage, then, well, what's happening, right? Obviously, it's not that 0 isn't really representative of what is taking place in a circuit. So this is where we get the RMS, because the fact is that power, if we remember from the power is current times voltage, and then the other triangle is voltage is current times resistance. So power equals IV, and V equals IR. So power is equal to I times IR, because current times voltage. Voltage is current times resistance, so I put the current times resistance into the voltage of current times resistance, which is I squared R. So if I look at what power I'm getting, that depends on the square of the current and of the voltage, since current and voltage are related. Well, if I look over here, that's 10 volts there. Well, if I square that, what's 10 squared? It's 100. Well, this is negative 10. What do I get if I square negative 10? Well, negative 10 times negative 10 is positive 100. And if I square 10 times 10, this is 100. And negative 10 times negative 10, this is 100. So each of these peaks of voltage, if you square it, and the square is what's important for the power, if you square it, you get a positive number. So even if the current is going back to positive, negative, the power goes from 0 up to some maximum value and back, okay? So power works more like this, because obviously 0 squared is 0. So that's 0, 0 squared is 0, 0 squared is 0, 0 squared is 0. So you get bursts of power at each maximum in the sine function. Okay, and you never have a negative power because power is current squared. So we get a value out of this, and it involves squares. Okay, so power is being delivered even though the average voltage is 0 and the average current is 0. Well, obviously the average power is not 0. So we need to have a way of representing the current and the voltage in an average form that doesn't give us a 0, because 0 makes no sense. All right, and this is where the root mean squared is. Okay, so if I wanted to take let me just pick these 4 values. Okay, 10, negative 10, 5, negative 5. Let's just take that. Okay, what's the average of those 4 values? Well, 10 plus negative 10 is 0, plus 5 is 5, negative 5 is 0. So it's 0. You average, you take 1, 2, 3, 4, add them up, 0, divide by 4, and the answer is 0. Okay, so that's the average. Okay, but as we talked about, the squares, if I square them, squares, the average, then square of 10 is 100. Square of negative 10 is 100. Square of 5 is 25. Square of negative 5 is 25. So add these up, and I got 100 plus 100 plus 25 plus 25 is 250. Divide that by 4. Okay. Well, 250 divided by 4 is, I should be able to do this in my head, right? But I want to pause it and use a calculator. Duh. Okay, it's 62 and a half. Okay, this is the average of the squares. Okay, that's the average of the squares. Now, if I then take the square root of this, okay, because these were all squared, okay, I squared that, squared that, squared that, squared that. I got the average of the squares. Now to get me back to something that is like what I originally had, like for example, if these were values in volts, like volts, 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 this would be volts squared, volts squared, volts squared, volts squared. So this is 62.5 volts squared. An average should be in volts, so I take the square root of this. So I take the square root of 62.5 volts squared, and that's equal to, back to the calculator, and that's equal to 7.9 volts. So the average of these 4 numbers is 0, but the average of if you take the squares, all right, take the values, square them, and then average the squares, and then take the square root. That is the root of the average or the mean of the squares, or RMS. That's an RMS value.